Hello everybody, welcome into another lesson. So today we are going to talk about what is called the fundamental theorem of algebra. The fundamental theorem of algebra, in short, states that the degree of the polynomial indicates the number of solutions in the complex number system. So up until this point we've only been concerned with the real solutions. But when we've done the rational zeros test and factoring and all that, we've only been dealing with the real solutions. We haven't known the whole story with the complex solutions. Well, the fundamental theorem of algebra covers the whole complex set, which would be your reals and your imaginaries. Now, to solve these equations, it's going to be the exact same as what we've been doing before, only today we're going to consider the imaginary solutions too. So let's get started here. I have about 8 examples of it. Alright, so let's see. We have f of x equals x to the 4th plus 5x to the 3rd plus 5x squared minus 5x minus 6, right? So we have x to the 4th plus 5x to the 3rd plus 5x squared minus 5x minus 6. So we want to find every x value for where the function equals 0. So basically you would just take what f of x is, set all that equal to 0. This one definitely can't be factored, so we're going to have to go for the rational zeros approach. So let's take our p over q, which would end up being, of course, factors of 6 for your constant terms. So you'd have plus and minus 1, plus and minus 2, plus and minus 3, and then plus and minus 6. Over the factors of your leading coefficient, which would be plus and minus 1. So therefore, your possible rational zeros are plus and minus 1, plus and minus 2, plus and minus 3, and then plus and minus 6. Alright, let's set up our synthetic division here and do some testing to see which ones work. So, coefficient of x to the 4th is 1, coefficient of x to the 3rd is 5, coefficient of x squared is also 5. Coefficient of x to the 1st is negative 5. Then your constant term is negative 6. Alright, so why don't we test positive 1? So bring down your 1. 1 times 1 is 1. 5 plus 1 is 6. 1 plus 6 is going to... 1 times 6 is 6. 5 plus 6, that's 11. 1 times 11, that's going to be 11. Negative 5 plus 11 is positive 6. Alright, so then 1 times 6 is 6. Negative 6 plus 6 is 0. Well, it looks like positive 1's the rational zero that works, so this is going to factor into x minus 1 times the quantity of x to the 3rd plus 6x squared plus 11x plus 6. So that's what this would factor into to start with. But the bad news is our cubic factor, it won't factor at all. So we're going to have to do the whole rational zeros thing yet again for the cubic. But the good news is, look at your coefficients on the cubic. They're the same, so you can literally keep them as the same as before. We'll have the same possible rational zeros. Alright, so coefficient of x to the 3rd is 1. Coefficient of x squared is 6. Coefficient of x to the 1st is 11. The constant term is 6. Alright, let's try negative 1. So let's bring down the 1 here. Negative 1 times 1 is negative 1. 6 minus 1 is 5. Negative 1 times 5 is negative 5. 11 minus 5 is 6. Negative 1 times 6, well, that's going to end up being negative 6. And then 6 minus 6 is 0. So we have a perfect factor. We have a perfect rational 0 of negative 1. So this will factor further into x minus 1 times the quantity of x plus 1 times the quantity of x squared plus 5x plus 6. So now we have two linear factors and a quadratic factor. Well, that quadratic factor will actually factor normally. That would factor into, you'll still have the quantity of x minus 1 times the quantity of x plus 1. Now the x squared plus 5x plus 6, this would be the quantity of x plus 2 times the quantity of x plus 3. All that equal to 0. Well, we have four linear factors now. And it factors no further. Now all you got to do is take each of these factors, set them equal to 0. So you would end up getting x equals negative 3, negative 2, and then both plus and minus 1. Those are all four zeros in the complex number system, and they all just happen to be real this time. But they're still part of the complex number system. So x would equal negative 3, negative 2, and then both plus and minus 1. So that was a relatively easy one because everything was in the real numbers in this case, but it doesn't always work out that way. Not always. Let's see what the next one looks like. All right, let's see. We have x to the fourth plus 4x to the third minus 6x squared minus 36x minus 27. All right, so we have f of x is going to be equal to x to the fourth plus 4x to the third minus 6x squared minus 36x minus 27. Well, this definitely isn't factoring again, so I think it's safe to say we need to do the rational zeros. So let's set up our p over q. The p over q, so the p is your factors of the constant term, so you'd have plus and minus 1, plus and minus 3, plus and minus 9, and then plus and minus 27. All that divided by the factors of the leading coefficient, which is 1, you would just get plus and minus 1. So your possible rational zeros are plus and minus 1, plus and minus 3, plus and minus 9, and then plus and minus 27. All right, so we're back at this again here with the synthetic division with our rational zeros. So coefficient on x to the fourth is 1, coefficient on x to the third is 4, coefficient on x squared is negative 6, coefficient on x to the first is negative 36, then your constant term is negative 27. All right, well, let's try 1. All right, so bring down your 1. 1 times 1 is 1. 4 plus 1 is 5. 1 times 5 is 5. Negative 6 plus 5 is negative 1. 1 times negative 1 is negative 1. Negative 36 minus 1 is negative 37. 1 times negative 37 is negative 37. Negative 27 plus negative 37 would be negative 64. So positive 1's definitely not a rational zero for this because we have a remainder of negative 64. And as we remember, in order for it to be a rational zero that works, we have to have a remainder of 0, which we clearly don't have in this case. All right, let's try negative 1. So again, bring down your 1. Now negative 1 times 1 is going to be negative 1. 4 minus 1 is 3. Negative 1 times 3 is going to be negative 3. Negative 6 minus 3 is negative 9. Negative 1 times negative 9 is positive 9. So negative 36 plus 9 is going to be negative 27. And then you end up having negative 1 times negative 27 is positive 27. Negative 27 plus 27 is 0. So that negative 1 is the rational 0 that works. So that means this is going to break down into x plus 1 times a cubic factor of x to the third plus 3x squared minus 9x minus 27. Whoops, I don't know where I got that 9 from. All that is equal to 0. Well, here's some good news about this. It looks like our cubic factor we can factor by grouping, right? We don't have to do the rational zeros with that, which will make life easier. So let's keep that x plus 1 outside of the bracket here. All right, now your first two terms, you could factor out a common x squared. You would get x squared times the quantity of x plus 3. Then for your second two terms, you could factor out a negative 9 times also the quantity of x plus 3. All that equal to 0. So this will break down into x plus 1 times the quantity. Let's see, you have a common x plus 3 for both of these terms, so you'll have times x plus 3 times the quantity of x squared minus 9. Well, that x squared minus 9 breaks down further into x plus 3 and x minus 3. So you'll have x plus 1 times the quantity of x plus 3, which will actually be squared, because one of the factors of x squared minus 9 is x plus 3. If you take x plus 3 times x plus 3, you get x plus 3 squared. Then times x minus 3. All that equal to 0. And when we get into the graphing section, which will be in the next two lessons, the final two lessons of the polynomials unit, we're going to talk about what it means when you have a factor to an odd power and to an even power in terms of graphing. But anyway, you'll set each of your factors equal to 0. You would end up getting x equals both plus and minus 3, where you have the negative 3 is actually two solutions because the factors of the second power. And then you have your positive 3, which occurs once, and then you also have a factor, you have an answer of negative 1. So x would equal plus and minus 3 and negative 1. Those would be your solutions to this particular polynomial. All right, what do we got? F of x equals x to the third, so we drop down to the third power for this, minus 4x squared plus 3x. Okay, this one doesn't look so bad. So we have f of x equals x to the third minus 4x squared plus 3x. We could definitely factor out a common x, right? If we do that, you'll get x times the quantity of x squared minus 4x plus 3, all that equals 0. And this quadratic factor does factor further. It's going to factor into x times the quantity of x minus 1 times the quantity of x minus 3. All that would equal 0. Then just set each of your factors equal to 0, so you'll get x equals 0, 1, and 3. And notice the degree of the polynomial is 3. We have 3 solutions here in the complex number system. So x would equal 0, 1, and 3 for your solutions. That one wasn't so bad. Next one, we have x to the third plus 5x squared minus 4x minus 20. All right. So we have f of x equals x to the third plus 5x squared minus 4x minus 20. This is one you can actually factor by grouping. Look at your first two terms, you can definitely factor out a common x squared, right? You'll have an x squared times the quantity of x plus 5. And then for your second two terms, you could factor out a negative 4, so you'd have negative 4 times x plus 5. All that equal to 0. Now between both terms, you have a common x plus 5, so go ahead and factor that out. You'll get that times your x squared minus 4 equal to 0. Well, the x squared minus 4 will factor further into the quantity of, we'll still have the x plus 5, but times the quantity of x plus 2 times the quantity of x minus 2. So we have three linear factors now. All that equal to 0. So that each of your factors equal to 0, you would get x equals negative 5, and then both plus and minus 2. And it turns out all three complex solutions, because the degree is 3, all three complex solutions were in the real number system. All right. Now, we have f of x equals x to the fourth minus 5x squared minus 36. So we have f of x equals x to the fourth minus 5x squared minus 36. Well, since it's an even power, it almost behaves quadratic-like. So this will factor down into x squared minus 9, that quantity, times x squared plus 4 would be equal to 0, right? Now notice the degree of the polynomial is 4, telling you have 4 solutions in the complex number system. Well, that x squared minus 9 factors further, right? It factors into x plus 3 quantity times x minus 3 quantity. Now, this is where I'm going to teach you about a sum of squares. We can, since we have the whole complex number system now, you can factor a sum of squares where we couldn't before when you only had the reals. If you take x squared plus 4 and set it equal to 0, what do you get? Well, you would get x squared equals negative 4, which would simply give you x equals both plus and minus 2i. So what does that mean? That x squared plus 4 will factor into the quantity of x plus 2i times the quantity of x minus 2i. All that equal to 0. So now we have 4 linear factors. So basically you treat it almost like you would a difference of squares. The only thing is you're going to have imaginary solutions. You write it as the sum and difference of the square root of x squared with an imaginary root of the number. That's all you would do. That's how you would factor a sum of squares. Now just set each of these equal to 0. You get x would equal both plus and minus 3, which are two different solutions. And then you get x would also equal plus and minus 2i. So those are all 4 solutions in the complex number system. X equals plus and minus 3, and then plus and minus 2i. All right. Another one here. So we have f of x equals x to the third minus x squared plus 49x minus 49. All right, so we have f of x equals x to the third minus x squared plus 49x minus 49. Well, I think it's fairly obvious we can do factoring by grouping, right? So look at your first two terms. You have an x squared in common. So if you factor out the x squared, you'll end up getting x squared times the quantity of x minus 1. And then look at your second two terms. You can factor out a common 49. So this will be plus 49, also times the quantity of x minus 1. All that equal to 0. All right. Well, you have a common x minus 1 on both terms. So factor that out, you'll get x minus 1 times the quantity of x squared plus 49. All that equal to 0. Remember, we have a sum of squares, which would just be x plus an imaginary root of 49 and x minus an imaginary root of 49. So this will factor into x minus 1 times the quantity of x plus 7i times the quantity of x minus 7i would be equal to 0. So now we have three linear factors in the complex number system, and that makes sense since the degree of the polynomial is 3. That's how many we should have. So set all of these equal to 0, you would get that x equals 1, and then both plus and minus 7i. So x would equal 1, and then plus and minus 7i. That's exactly what you would get. Should only have a few more here. Maybe like 2 more. Yeah, let's do 2 more. So f of x is going to equal x to the fourth plus 6x to the third plus 14x to the second plus 54x plus 45. All right, so f of x equals x to the fourth plus 6x to the third plus 14x squared plus 54x plus 45. Well, it's definitely not factoring, right? So we're going to have to do the whole rational zeros thing. So let's go ahead and take our p and q. P over q, which factors of the constant term 45, of course you have plus and minus 1, plus and minus 3, plus and minus 5, then you have plus and minus 9, then you have plus and minus 15, then of course you have plus and minus 45. All over the factors of your leading coefficient, which would just be 1, so plus and minus 1. So your possible rational zeros are plus and minus 1, plus and minus 3, plus and minus 5, plus and minus 9, plus and minus 15, and then plus and minus 45. All right, let's begin the synthetic division and see what we come up with here. Coefficient of the x to the fourth term is 1. Coefficient of x to the third is 6. Coefficient of x squared is 14. Coefficient of x to the first is 54. Coefficient of, the constant term is 45. Well, let's just look at this here real quick. If you take any positive rational zero, you're always going to get a remainder, right? Because everything's positive. So that cuts this list in half. All that's really going to work are negative rational zeros. So let's try negative 1. All right, so bring down your 1. Negative 1 times 1 is negative 1. 6 minus 1 is going to be 5. All right, negative 1 times 5 is negative 5. All right, 14 minus 5 is going to be 9. Negative 1 times 9 is going to be negative 9. All right, so 54 minus 9 is 45. Negative 1 times 45 is negative 45. So then you would get 45 minus 45 gives you 0. Well, negative 1 is the rational 0 that works. So this is now going to factor into the quantity of x plus 1 times the quantity of x to the third plus 5x squared plus 9x plus 45. All that equal to 0. And the good news is our cubic factor, we can actually totally do that by grouping. So let's go ahead and do that here. So keep your x plus 1 outside of the brackets. Now between the first two terms of the cubic factor, you have a common x squared. You'll have that times x plus 5. Then you have a common 9 between the 9x and 45, so that would be plus 9 times the quantity of x plus 5. All that is equal to 0. Now, if you look inside of the brackets, you have a common x plus 5 on both terms. So you'll end up getting x plus 1 quantity times the x plus 5 quantity times the quantity of x squared plus 9 equal to 0. Well, that x squared plus 9 is a sum of squares. So what you're going to have now is the quantity of x plus 1 times the quantity of x plus 5 times the quantity of x plus 3i times the quantity of x minus 3i. All that is equal to 0. Now just set each of your factors equal to 0. So you should get x equals negative 5, negative 1, and then plus and minus 3i. So those are all four solutions in the complex number system. And the degree of the polynomials to the fourth power, so that makes sense. Therefore, you have four solutions in the complex number system. So x would equal negative 5, negative 1, and then plus and minus 3i. I got just one more, then we're done for the day. All right, last one. So f of x equals x to the fourth minus x to the third minus 5x squared minus x minus 6. All right, so f of x equals x to the fourth minus x to the third minus 5x squared minus x minus 6. The degree of the polynomial being 4 tells you we should have 4 complex solutions. So definitely not factoring, so we're going to have to use the rational zeros test. So take your p over q, p being the factors of your constant term of that 6, so plus and minus 1, plus and minus 2, plus and minus 3, and then plus and minus 6. All that divided by factors of your leading coefficient, which would be 1, simply plus and minus 1. So your possible rational zeros are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. All right, let's do our synthetic division now and see what we come up with. All right, coefficient on x to the fourth is 1. Coefficient on x to the third is negative 1. coefficient on x to the second is -5, coefficient on x to the first is -1, and then your constant term is going to be -6. Let's try +1 as a rational zero. So bring down your 1 here. 1 times 1 is going to be 1. -1 plus 1 is 0. All right. 1 times 0 is 0. So -5 plus 0 is -5. 1 times -5 is -5. -1 plus -5 is -6. 1 times -6 is -6. Well, -6 minus 6 is -12. We have a remainder of -12, so that's definitely not going to work. All right, so what if we try -1 this time? Bring down your 1. -1 times 1 is -1. -1 minus 1 is actually -2. -1 times -2 is +2. Now -5 plus 2 is -3. -1 times -3 is +3. -1 plus 3 is +2. -1 times 2 is going to be -2. -6 minus 2 is -8. We still have a remainder of -8. That's definitely not going to work. Well, we have up to 6 more rational zeros to go still. Hopefully it won't take that many. Sometimes the smaller numbers can be deceptively difficult because the coefficients didn't look too bad on this one, but don't let it deceive you. It could be trickier than it looks. Let's try +2. So bring down your 1. Now what's 2 times 1? That's 2. -1 plus 2 is +1. All right. 2 times 1 is 2. -5 plus 2 is going to be -3. 2 times -3 is -6. -1 minus 6 is -7. 2 times -7 is -14. All right, -6 minus 14 is -20. Well, we have a remainder of -20. That's definitely not going to work. So we tried +2 as a rational zero. Why don't we try -2? All right, let's try it. -2 for that. So let's bring down your 1. -2 times 1 is -2. -1 minus 2 is -3. -2 times -3 is +6. Well, -5 plus 6 is +1. -2 times 1 is -2. -1 minus 2 is actually -3. -2 times -3 is +6. Well, -6 plus 6 is 0. So -2 is the rational zero that's going to work since we got a remainder of 0. So this will now factor into the quantity of x plus 2 times a cubic factor of x to the third minus 3x squared plus x minus 3 would equal 0. Well, good news is your cubic factor, we can definitely solve, we can factor that by grouping, right? So keep your x plus 2 outside of the parentheses, outside of the brackets rather. Your first two terms, you can factor out a common x to the second. That'll give you x to the second times the quantity of x minus 3. Then plus you'll just have a quantity of x minus 3. All that equal to 0. Well, inside the brackets, what do you have common to both terms? You have an x minus 3, don't you? So this will factor into the quantity of x plus 2 times the quantity of x minus 3 times the quantity of x squared plus 1. Well, x squared plus 1 is a sum of squares. So what you're going to have now is x plus 2 times the quantity of x minus 3 And then that x squared plus 1 will factor into the quantity of x plus I times the quantity of x minus I. All that equal to 0. Now set each of these four factors equal to 0, you would get that x equals -2, +3, and then both plus and minus I. So you have four answers here in the complex number system, and that makes sense since the degree of your polynomial is 4. So that means if it were to the 7th power, we should have 7 solutions in the complex number system. So that's it for this lesson. The last 2 lessons of polynomials are going to be about graphing. Next lesson should actually be super easy. We're just going to talk about the end behavior of polynomial graphs. And then the lesson after that, we'll get more into detailed graphing of them and what how you graph at the intercepts and what even and odd power factors mean and all that. So I hope everyone has a great night. Take care.